Okay. This is the harder physical pendulum problem I've been talking about. Pendulum. L-U-M. Okay. So, first, I'll show you the problem. A small ball of mass big M is attached to the end of a uniform rod of equal mass big M and length L that is pivoted at the top, meaning one of its ends. Calculate the period of oscillation for small displacements. So first, a sketch. We're going to have our rod, which is skinny but does have mass. It has a mass M, and then on its end is a small ball also of mass M. And we are pivoting up here at the top, so pivot. We also know the length of this is given as L, and we need to try and figure out what is going on. So things we know, it's going to be set up to make an angle theta. If it's a uniform rod, then we can think about the gravitational force as acting from its center, and the ball on the end, we can think of it as having a gravitational force acting from its center. So, first step. We want to find the torque due to each part. Okay, well, let's see. We've got this first part, the rod. Oops, I want to write it as a tau. So the torque of the rod, it's acting at a distance L over 2 away. It has a gravitational force of mg. We want the component that would be perpendicular, so we need a sine of theta component, and it will oppose whatever theta is in. If theta is positive, then it will be in the negative direction. We also need torque for that ball on the end. Notice it is a distance the whole length away. It has a gravitational force mg. We still have to think about components, so we've got a sine of theta. And it's going to be opposite whatever theta is. If theta is positive, the torque will be negative. If theta is negative, the torque will be positive. So it's always in opposition. Alright, now that we have that, we need to find the sum of the torques. Okay, that's pretty easy. We've got a, minus L over 2 big mg sine theta, and we've got, a minus L mg sine theta, and all of that will be equal to I times alpha. So let's see, the mg is common. Factor it out. And that'll be a minus 3/2 mg sine theta equals I times alpha. 2 steps down. Step 3. Find the total moment of inertia. Alright, I'm going to take a moment to do this properly. We have a skinny little rod, and we've got the pivot at one end. We'll set that as x equals 0. The other end will be at x equals L. We're going to look at a point somewhere partway along this at x. And we want to find I is equal to integral of r squared dm. dm is going to be the linear density times dx, the length of a small piece of this. So this part, the density will be m over L, then we'll have the dx. R is being mapped to x here, so for the rod, we've got an integral from 0 to L of m over L with the x squared and the dx, which is pretty easy. The m over L can come out in front, integral of x cubed dx. Oh, sorry, x squared dx. From 0 to L. And that will mean the moment of inertia for the rod will be m over L times, let's see, that'll be L cubed over 3 when we're all done, so 1/3 mL squared. Now that's just the rod. We also have that ball on the end, and it is small, so we can treat it just as a particle. And since it's all the same distance away, that means it's just an mL squared. That makes the total 1/3 mL squared plus mL squared, which is, well, let's see, that's going to be a 3 over 3 with a common denominator, so 4/3 mL squared. Alright, so we're about to take our torque equation and our I total and put them together. So the next step bring all the parts together. So now we will have, let's see, it was a -3/2, yep. -3/2 L times m times g sine of theta equal to 4/3 mL squared alpha. Cancellations. The m cancels out, which is pretty typical for physical pendulum problems. We'll be taking advantage of that probably in the lab for our oscillations here. Okay, with all that cancelled out, what's left? -3/2 g sine theta and 4/3 L alpha. Let's put it in standard form. 4/3 L alpha plus 3/2 g sine theta. Divide through, well, multiply through by 3/4 and divide through by L to get the alpha on its own. So we now have 9 over 8 g over L sine theta is equal to 0. Okay, we're almost done. So small deflection. Sine theta will be equal to theta. And now it's in pure standard form. So alpha plus 9/8 g over L theta is equal to 0. We can assume our standard solution, a cosine of omega t plus a phase. So that means alpha will look like -a omega squared cosine of omega t plus phase. And in the end, that lets us find our omega, because the a and the cosine omega t will cancel out once we plug in. Oops. All right. There we go. And we were asked to find period. 2 pi over the period is omega. which is equal to the square root of 9/8 g over L. So the period must be equal to 2 pi, the square root of 8L over 9G. I think that's it anyway. Let's see, so yeah, we can do a little bit of factoring here. So the 8 can be factored into a 4 and a 2. And the 4 is a pair, so we can bring a 2 out. So it would be a 4 pi. The 9 is a perfect square, so we can bring a 3 out. And either of these ways of writing it would be perfectly acceptable. Okay. So this was a harder example, and like I said, rather than just using omega is equal to the square root of x center of mass m g over I, you'd have to have been very, very careful to get it right here. The I would come out the same. If you find your x, it actually comes out as 3/4 L. Try it and figure it out for yourself, because one of them has its center of mass at L over 2 and the other one at L. Each one has a total mass m. The total mass is 2m. Then you'd have your gravitation constant. Then you'd get exactly the same I. That won't change. So it would still be 4/3 ml squared. It is the same amount of work really mathematically either way, but I find personally it is much easier to not forget things like the 2m if you do it this step-by-step way that I have just laid out. Find the torque due to each part, find the total torque due to all the parts, find the total moment of inertia, bring it together, put it in normal form, and find your answer. Okay. So that's it for the harder problem. Hopefully we'll have a harder problem like this, similar to this, to try in class together. But that's going to be it for this video, and I will see you in the next video, which I think is going to be damped harmonic oscillations. So damped harmonic motion, which is a close relative of simple harmonic motion, but as you might imagine, allows the amplitudes to die away over time, which simple harmonic motion doesn't do.